It's always very special to stand or address the Royal Institution. For a physicist, one always thinks back to Michael Faraday. This is a book that I treasure, his Christmas lectures about the natural history of a candle. And it makes great reading even today. And if I think if Faraday were alive today, he could probably would not want to talk about candles, but he might talk about he might give a heck of a cooking show about the chemistry of cooking, and especially microwave cooking, which is based on his work. In any case, Sir Michael, this is for you. And in the book Fundamentals, I really went back and thought about the questions that motivated me to get into science in the first place, the kind of philosophical questions. What is the nature? What does it all mean? What is the nature of reality? The kinds of things that teenagers ask. And that in the everyday work of science kind of are in the background. But over the course of my career, I do feel I've learned a lot, and it was time to share and also bring it all into clarity in my own mind. And so an alternative title, and the title of tonight's lecture, would be What Reality Has Taught Me. So I wanted to show you some of the themes, the main themes that emerge from the fundamental understanding of reality, at least in my experience. So one lesson that one learns is humility. This is a familiar picture of, perhaps to some of you, of the Earth from the surface of the moon. And from the moon, the Earth looks very beautiful. The sky is, you'll notice, is black because there's no atmosphere. So it's very dramatic. And the Earth itself is reflective and patterned. So it's beautiful. But the main thing you would notice is that it's really small. It appears as just a little bit larger than the moon appears in our sky. The Earth would appear from the moon, in the moon sky. And of course, the moon is our closest neighbor in the solar system. The solar system as a whole is much larger. And the solar system is a minuscule part of our Milky Way galaxy. The Milky Way galaxy contains billions of stars like the sun. And then on top of that, when you look out with a deep space telescope, with the Hubble Space Telescope, this is a very small part of the sky. And what you see is that if you look with penetrating eyes deep into the universe, you see a whole sky full of not just stars, but whole galaxies. Each of these extended objects is a galaxy, and many of them are equal to or greater than the Milky Way in terms of the amount of mass and the number of stars they contain. So all the struggles of mankind, all the struggles of daily life are taking place in a very, very small part of the universe. And that's a cause for humility. As for space, so also for time, one way of bringing that down to proportions that we can understand is to map cosmic time in a linear fashion just by rescaling it onto a year, a time we can comprehend, 1 year. Cosmic time back to the Big Bang is 13.8 billion years. So if we count that as January 1st, At first, it's a very hot and inhospitable place. Sort of uniformly lit up, very nearly uniformly bright, like the inside of a neon light. But then things calm down a little bit into separate bodies. And the first signals of that we see are gamma ray bursts. On January 22nd, galaxies start to form. Our own galaxy is not but the first by any means, not even in the first generation. It's on the 16th of March. And Earth, and something like the form we know it, is already taking us deep into the fall. 4.4 billion years is the oldest rocks on Earth, and that gives a pretty good indication of when the Earth cooled down, became solid, and was a place where life could possibly maintain itself. And sure enough, in a few days on this cosmic scale, life did emerge, but that's already very simple forms of life in 14th of September. I won't go through this whole history, but just to note that God gave us a Christmas present on the 25th by wiping out the dinosaurs, rough on the sort of right after, on the border between the 25th and 26th. And human history, as we know it, the dinosaurs were wiped out arose on Christmas and were wiped out on the last day of the year. And it's only then that mammals snuck out from their hiding places and their nocturnal ways, and human history is compressed well within the last day and a half of this cosmic history. So that's plenty of reason for humility if you just judge our significance in the universe in terms of how much space we occupy and how much time we survive as individuals or as all of humanity. On the other hand, there's good reason for chutzpah. Chutzpah is a word that may not be universally familiar. It's a word from Yiddish that means audacity. So it means insolence or cheek, I guess is the British word that corresponds. And there's plenty of reason for chutzpah too. And chutzpah has been a very successful approach to the universe. And it has an objective basis. This is a sketch of something each of us has within our skulls. This is the hippocampus, sketched by the great neuroanatomist Ramon Cajal. The human hippocampus is where short-term memories are processed into long-term memories. It's also the place where a lot of our sense of orientation and position in space is housed. So it's a very powerful little processing unit inside our brains. You can see it has a regular structure with many, many, many components. In fact, this method of staining that was used to make the hippocampus look like this is, but I mean, the way Ramon Cajal could get an image of the hippocampus that he could sketch, that wasn't just black on black, so much complexity that there's nothing to see, is first of all by taking a very, very thin slice, and secondly by applying a dye which stains approximately 1 in 1,000 cells. So the complexity of this, if you included more layers and didn't select only 1 in 1,000 cells, you can imagine. And even as it is, you see that within ourselves, we have enormous resources. So we are small compared to the universe, but we are large compared to what it takes to have complex patterns and process them dynamically in time. So in that sense, Walt Whitman was right that he contains multitudes. And this sort of tension between humility on the one hand and the sense that we can have the audacity to live in the universe and attempt to understand it was already articulated by Blaise Pascal when he said the spaces of the universe enfold and swallow me up like a speck, but by the power of thought, I may comprehend the universe. But Pascal flourished in the 16th and 17th century, where science was still relatively modest in its accomplishments. So his was intuition, an intuition that the universe could be comprehended. And I think probably what he meant by comprehended is just that you could look at it all, look out there and get an idea that it was much bigger. Einstein, who in the 20th century saw much more of the development of science, and he, of course, he did not have access to the Hubble Space Telescope or to our modern understanding of fundamental physics. He was groping towards unification and only knew about two of the four forces we know about, and we've made enormous progress since then. He struggled with quantum mechanics, and now we're learning to really apply it in great detail and control it to put it to work. But in any case, Einstein articulated the same thought, that the most incomprehensible thing about the world is that it is comprehensible. That was also, I mean, it's easy for someone to say that, but that also has an objective correlate. If you, one measure of how well we comprehend the world is how well we can act on it, how effectively we can act on it. And if you look at the chart of human wealth, it's how much we're able to create in terms of take the universe as it is and make it useful to our own purposes. This is somewhat of an art to estimate exactly what that means, but economists have tried to formulate a good definition of what world GDP per capita means and trace it historically. And you can argue about factors of two here, but the overall trend that human productivity was pretty much flat over most of history and extending and very, very slowly increasing at best until with the rise of scientific methods and technology, it's taken off exponentially and there's no end in sight. So we really do comprehend things. It's not just that we've come to peace with our lack of comprehension, but we prove our comprehension by being able to act effectively. So those are the two big lessons. Another big lesson that I've learned is that answers breed questions. I'll give you just two examples of that. So our comprehension is impressive, I hope I've conveyed, but it's incomplete. One way it's incomplete is that astronomers have learned that there's a component of the universe that we don't understand that actually by mass outweighs the part we do understand by about a factor of 5. This is the so-called dark matter. The methods that are used to uncover that there is dark matter are advanced methods of astronomy and things like seeing how light is bent by the distributions of matter and seeing that there has to be more matter than we know how to account for. And we have ideas about what that might be. We have very attractive theoretical proposals. Something I called Axions is a leading proposal. And we have, since we have equations for how axions are supposed to behave, we can design antennas that are capable of detecting it, of turning it into signals that we can see. And this is a representation of how better understanding of the universe has led us to new questions and new methods of addressing those questions that will bring more of the universe into our conscious awareness and control. Another frontier of questions that we're beginning to approach is understanding the basis of mind in matter. So we now have, I think it's hard to question, although one can question, but it's hard to question successfully, I would say, an understanding of the kind of matter that supports biology and chemistry and geology and all forms of engineering and almost all of astrophysics and cosmology, that's detailed and complete and well tested and gets down to more accuracy and accuracy to spare and tested to spare for all those applications. So we can then, we have the fundamental basis to see whether, like the phenomena of metabolism and heredity, which have now been understood on a molecular basis, whether mind can also be understood on a molecular basis. So our knowledge of how this I is based in matter is kind of beginning to pose questions that can be answered and closing the loop. Another thing that I like about this picture that is due to John Wheeler is that it also alludes to the fact that we understand in broad outlines the history of the universe that can give rise to this brain. So we're both understanding where we came from at the level of history and understanding where we came from and what we are at the level of fundamental laws and matter. Another great lesson that I've learned from reality is kind of a meta lesson that I call called complementarity. This is the idea that different ways of viewing the same thing can be both informative and both valid, and yet difficult or impossible to maintain at the same time. This is a kind of theorem in quantum mechanics. You cannot understand quantum mechanics without complementarity, because the ways of answering different kinds of questions, for instance, questions about position versus questions about velocity, require processing the fundamental reality, in this case, the wave function, in incompatible ways. That's the origin of Heisenberg's uncertainty principle in the formalism of quantum mechanics, and the origin of Bohr's principle of complementarity, which he took from in quantum mechanics out into the world of philosophy and world understanding in general. To me, a beautiful example of complementarity that kind of brings it down to earth, and actually corresponds in the mathematical formalism very closely to this complementarity of quantum mechanics that I mentioned, is in a piece of music, you can analyze it either in terms of the harmonies it contains or the melodies it contains. But you can't really do both at once. If you're going to do the harmonies, you have to pay all equal attention to all the voices at once. If you're going to look at the melodies, you have to disentangle the voices and look at it sort of horizontally, integrating over time as opposed to taking slices in time. Another memorable example of complementarity that I really like. It's simple-minded and funny, but really profound in a way. Is this object a rabbit or a duck? Well, it's both, but only one at a time, and that's an example of, to understand it completely, you have to take different points of view, and each one is informative, and yet each one excludes the other. And only by expanding your mind and allowing yourself to analyze and think about things in different ways do you do full justice to the underlying reality of things. And to me, this spirit of complementarity leads to a different way of understanding the tension between free will and determinism, for instance, that does not lead to just pointless discussions that go around and around in circles, but accepts both as answers to different kinds of questions. It's a liberating, mind-expanding attitude towards the world that you can take from fundamental understanding of the world out into experience and life and wisdom. So that's a small sampling of what reality has taught me. There's lots more, and I wanted to open this occasion to discussion, and I hope there'll be questions and challenges and explorations to follow. But just let me tell you that there's lots more in this book that just is being released today in the US well, on Amazon, so you can get it, and it expands greatly on those and other fundamental lessons that I've learned from reality. And let me just quickly go through without detailed discussion, but so that you can ask about them more and also get a sense of what is taken up in the book. There are 10 assertions, which are these 10 keys to reality, and they are: there's plenty of space, both external and internal. We talked about that. And similarly, there's plenty of time, both external and internal. I analyze the speed of thought and then quantify how many thoughts you can have in a lifetime, and there are billions. So there's plenty of time, even though we live a short time compared to the universe. There are very few ingredients. We learn that the world is made out of just a few things that have very special, understandable properties. There are very few laws that tell us how they behave. And there's plenty of matter and energy. The universe is large, not only in space and time, but also in terms of the resources that we can tap into. So if we don't blow it, humanity can have a very bright future. So that kind of is about the fundamentals of what there is. And then in the second part of the book, I discuss sort of how they act in the world, how they have acted, and some ideas about how they will act and how one should understand it going forwards. So one big lesson is that cosmic history is an open book. We really can penetrate back to the very, very early history of the universe with observations and evidence and piece together a broad history of what happened and how we got here. But we also learn that that does not account for everything. The simple laws and simple beginnings don't tell us about the details of what emerges. There are fundamental limits to how much you can extract from fundamental understanding. Things like quantum mechanical uncertainty and chaos intervene, and we can understand how complexity emerges, so that, for instance, the history of England can be much more complicated than the history of the universe. We understand that there's plenty more to see. The fundamental understanding teaches us that our senses reveal only a small part of what's out there, but they also reveal ways we can try to improve on our understanding, on our access to reality. And we can do that in small things like timekeeping, that watches that we carry around, but also in advanced projects that open us up to seeing things like gravitational waves or Higgs particles, and hopefully the dark matter. Mysteries remain, and complementarity is mind expanding. So I hope I gave you a sense of what I've learned from reality and what I've tried to share in fundamentals. So with that, I'll open things up for questions.
Wow, thanks very much, Frank. Normally, regular viewers will know that we sometimes play a big video of applause happening, but unfortunately, due to the new platform, that hasn't happened just yet. But thank you so much for that talk. We've had quite a few people in the chat asking various questions. I just want to say something before I launch into the questions. I do want to apologise because we had a little bit of a bumpy a bumpy start to the stream. I forgot to read out some other things that I was going to let people know about you. So what I was going to do before I kind of panicked and just threw to Frank straight away, because I was slightly nervous. I was going to read you the top 3 comments on Frank's previous YouTube video, because I think they'll give you, you can look up his academic CV anyway. You can look at the many prizes and professorships he has. But I thought you might enjoy what the general public, the people out there, say about him. So he, comment 1, this guy gives amazing lectures. His calm, precise voice is hypnotic. The second one says, Wilczek is brilliant. His book, The Likeness of Being, is a great start for anyone who wants to stand the strong force via quantum chromodynamics. And finally, seems like a pretty cool guy. I'd like to see him do a cooking show. So there's the full range of opinions.
That last one I was anticipating. Yeah, that last one I was anticipating, because we talked about it before, and that's what led me to think that, gosh, Faraday could have given a heck of a cooking show, and I'm sure he would have really enjoyed talking about microwave ovens, since they come from his work on electromagnetism pretty directly.
Yeah, so sorry about that, everyone, for the rather bumpy start. Just let's go to some actual questions about physics, shall we? So Mohammed asks, is there any reason to doubt the cosmological timeline? Is it definitive the way it stands? I know other timelines that we have, like the timeline of human evolution and a few other things, are kind of a bit contested, and we're not quite sure where did Neanderthals fit in, and we have sort of ideas. But are we sort of pretty certain with the cosmic microwave measurements and other things that we can go, yep, 13.7 billion?
It's pinned down pretty firmly. I think all the events that I noticed, certainly I didn't pore over that timeline in great detail, I have to confess. But all the events that I noticed were certainly well pinned down by a variety of techniques, looking at redshifts of different objects versus time, which tells us how fast the universe, how big the universe was at different stages, and how fast the galaxies were receding. Looking at radioactive dating, which tells us about old rocks and also about events of more recent history. Looking at stellar evolution, which you can look at stars with different colors doing different things in different places and figure out how old they are. There are many lines of evidence that firm up this picture, and you alluded to the microwave background radiation. So that gives us sort of actual images of the early universe from which you can infer a lot of what happened, what was happening at the time the snapshot was taken, so to speak, but also what happened before, with very plausible extrapolations of the laws of physics that we can, some of whose consequences we can check. Now, one thing that is not certain, though, at all, to put it mildly, is the very beginning of that timeline. What happened 13.8 billion years ago is that the universe became very, very dense and very, very hot, we think. But what happens is not that we know that it emerged from an explosion, but that we know our equations break down. We know the experimentally verified parts of our description of the world that work up to a certain energy could have surprises if we extrapolate to higher energies and higher densities than they've been tested. And in a way, we know that something has to give, because if we take things back far enough, and going backwards in time, the universe gets smaller and smaller and hotter and denser and denser, the equations just become infinity equals infinity. They break down, they become mathematically singular. So at some point, you shouldn't think of that endpoint as an endpoint. What it means is that our equations stop working. It doesn't mean that the universe stopped working or that it emerged from some kind of truly singular event. The fact is, we don't know very well what happened, and we have some hope that by studying gravitational radiation, which because it interacts so weakly with ordinary matter, can sort of shine through in a way to the earliest universe in a way that other signals can't, because the photons get scattered and scrambled and so forth. That we'll be able to look back further, but we're just getting the technology now to see those kinds of gravitational waves. I mean, precisely because they do interact so weakly with matter, it's a tremendous feat of technology to detect them at all. And we have some theoretical ideas about what might have happened, the so-called inflationary universe, but there's kind of circumstantial evidence that understanding can be extrapolated very far back, but ultimately we don't know what happened. But we don't know the very beginning. We don't. So that there's certainly room for surprise there. Nor, of course, do we know the end. that the year. Hopefully, this year is not the only year of cosmic history, and it's very interesting to think what's going to happen on cosmological scales in the
as you say
forward,
that.
Right?
Zenergy in the comments actually says that according to the 24-hour clock analogy, we will flip over to a new aeon, as Roger Penrose's theory suggests. I think he has the cycles of time theory. I don't know if you know about that. Would you like to comment on it?
It seems far-fetched to me, but he's a smart guy.
I find that about Roger Penrose as well.
More in it than I've been able to see. What?
That's why I was hoping you'd help me out, because it seems crazy, but he's so many times more intelligent than I am that I don't know.
Let me just say that his picture is imaginative and kind of attractive on broad philosophical grounds as a logical possibility, but it is not a straightforward extrapolation of physical law as we know it. On the contrary, it would require changes that at present there's no real evidence for. But,
so while we're on the structure of the universe, what was I going to say? How would you explain the kind of the matter antimatter imbalance? Obviously, after the Big Bang, that we have more matter than antimatter, because I'm made of matter. But how can looking at the history of the universe explain that?
Okay, well, first of all, we have to establish the idea that there should be balance between matter and antimatter that to explain why. And I guess we have intuition that the universe might have been ideally simple and maximally symmetric early on. And that would suggest that there should be equal amounts of matter and antimatter. But you can be more precise about it. If we extrapolate the Big Bang to very, very high temperatures and take the laws as we know them, eventually the reactions are such that you produce lots of, if we run it backwards, you would produce vast amounts of antiparticles together with particles in pairs. And so you'd have, in equilibrium, you'd produce you'd have equal amounts of matter and antimatter. So it really is not just a nice thing, but kind of mandatory to start with a balance between matter and antimatter at the very beginning, or as far as we can take it towards the beginning. And then you have to run things forwards in time to see how from that condition of symmetry, an asymmetry developed. Now, the first thing to say about that is that the asymmetry between matter and antimatter on cosmic scales is actually a very small effect. If you compare the number of photons which are out in the microwave background radiation, which is a measure of how many sort of net particles there were early in the universe, when the microwave photons first began to penetrate and be observable from, so the universe became transparent to that kind of radiation as it is now. Compare the number of those kinds of photons to the number of quarks in the universe, or the number of electrons, you find that the number of photons is about 10 billion times as much. So that the matter, as we call it, represents an imbalance of about 1 part in 10 billion. You started with very, very large numbers of quarks and antiquarks comparable to the number of photons, but almost all of them annihilated, and what's left over is just 1 part in 10 billion. So we have to explain a very, very small imbalance that gives rise to the universe as we see it today. Now, our control over fundamental physical law is not really good enough to quantitatively address that imbalance and how it arose, but we do have pretty good ideas. How should I say? It doesn't make a crisis in fundamental physics, because we have pretty good semi-quantitative ideas about interactions that have a little bit of imbalance between how they want to produce matter versus antimatter. Ideas about how those reactions would have played out, calculations about how those reactions would have played out in the evolution of the universe. And you can get, you can get the right answer, but the inputs are so uncertain that it's not so impressive that you can get the right. You can get the right answer in several different ways, at most one of which is correct. So it's not a crisis, but it's kind of a somewhat unsatisfying situation that we have a rough understanding of how that asymmetry could arise, and within the framework of the fundamental laws as we know them, but not a precise understanding. And unfortunately, not much prospect of getting a precise understanding, because we believe most of us believe that the processes involved are revealed only at much higher energies, and involve much heavier particles than we can actually produce at accelerators in practice.
So actually, David asked a follow-up question where he was basically saying, is it supposed to kind of uniformly distributed, this tiny imbalance, or is it kind of localized? Are there clumps of antimatter out there, and is it kind of, because the universe is fairly clumpy generally, isn't it, as a structure?
It's very clumpy generally, but there's no evidence for significant parts of the universe that are composed of antimatter, and there are very strong arguments against it. Those regions of the universe, if they existed, well, first of all, the most obvious evidence is not evidence. You might say, couldn't we just see that it was antimatter? And you can't, because what we see is photons, for the most part, and photons are their own antiparticles. So the photons produced by antimatter would be very nearly exactly the same photons that you would see from matter. So just by looking, you can't tell. However, if you have some regions where there's matter and some regions where there's antimatter, where they collide, so to speak, the border regions would be very hot and emitting a lot of high energy radiation, because the matter and antimatter would be annihilating there. So there's no evidence for that. There's also, if you don't look at photons, but look at cosmic rays, which involve typically protons and electrons and matter, there's only a very small amount of antimatter in the cosmic rays, and we can account for that in terms of secondary production of antimatter. So there don't seem to be any. It's very hard to think that there are parts of the universe that are made out of antimatter. It's really not possible to accommodate within within astrophysics as we know it. And so, we believe and have tremendous evidence for the idea that the universe early on was much more homogeneous than it is today. The microwave background radiation, for instance, which gives a snapshot of the universe when it was about 100,000 years old, so 100,000 years after the Big Bang, is uniform to within a part in 10,000, roughly. So there were no galaxies, no clumps, no black holes, just kind of a uniform haze.
So that was gravity, basically, pulling everything together.
And then gravity magnified very small density contrast. So I like to say the rich get richer and the poor get poorer. The parts that had over densities of matter have more gravity and pull in more and get even more dense, and the left behind places don't get thinned out, and so that's in very broad terms how galaxies and then planets and things get formed.
So I've got a few more questions here. I've got quite a few more physics questions, but I'm going to give you a break from physics, because if you are going to publish a book with such a wide outlook, you've got to expect questions on lots of other subjects as well, I'm afraid.
To me, well, physics has a hard core, of course, but physics really is about the world. And my big aspiration in this book, and my big aspiration really in life, is to understand reality, and physics is a tool for that. Yeah.
And I absolutely think that's where the idea of complementarity comes in. Like, I can, look at this, painting on my wall and go, well, that's got this pigment and this kind of canvas, and analyze it chemically, or I can analyze it artistically, and both is correct, but I'm just looking at the same thing.
Both are correct, right?
It tells me different things.
Keats famously bemoaned that the scientists had taken the magic out of a rainbow, but I think that's totally wrong. When I see a rainbow, it just looks just as beautiful as it ever did, and in fact more beautiful, because now I understand how it arises, and I can make my own rainbows with prisms or glass or water droplets, and they can understand why it is, and it enriches understanding. And similarly, I feel by understanding electronics, I have a different relationship to my computer than otherwise, and so on. It enriches your experience of the world to know how things work.
So on that, we had when you mentioned GDP earlier, we had a few people in the chat talking about GDP, and is it really a good measure of well-being, or is it what is it actually measuring? And I think you used it specifically to measure productivity. You actually said productivity rather than
Well, it's called, it's
happiness or
GDP. This is kind of out. I don't know exactly. I have to confess, I don't know exactly what one goes into that measure of GDP. It's a construct of
yeah.
economics, and that's why I say I wouldn't be surprised if different experts came up with different estimates that differed by a factor of 2 or something. But broadly speaking, another measure that's more objective, and I think gives more or less the same answer, is how much energy per human is being used, how much energy is being generated and used in industrial processes and just everything. How much energy does humanity control and put to its own use? And there's a baseline, which is based on agriculture. We use the energy to fuel our bodies, and for a long time, that was the main economic activity, and so the GDP was flat at just enough to keep us going, to keep the lights on in our brains, which is about 30 watts, and support and heat our bodies and metabolism, which is about 5 times more. And there wasn't much of a surplus, but now we control energy to make things for industrial processes, and you can quantify how much energy, and it's about, if I remember correctly, I discussed this quantitatively in the book, but I think in advanced countries, it's something like 100 times the baseline. And for humanity as a whole, it's something like 50 times the baseline. So that's an objective measure of.
So another person, I forget the name actually, but it was a really interesting thing to bring up. Mentioned title of an article from 1960 called "The Unreasonable Effectiveness of Mathematics in the Natural Scientists."
Oh yes,
published by Eugene Wigner, which seems to be a kind of a similar kind of path that you're treading here, the side. And so for those that don't know, and for me that's just read up about it, he basically observed that his theory was that the mathematical structure of a physical theory often points the way to further advances in that theory and even to empirical prediction. So by kind of putting something into a mathematical form, you can then learn something from those sort of equations. I just wondered if you'd read it or you had any thoughts on that idea.
Well, it's really the theme of my previous book, was how beauty, in a broad sense, has led us to deeper understanding of the physical world. That's the theme of this book is kind of, broadly speaking, the other direction, how understanding truth leads us to beauty, or at least enriched understanding of the world, and more wisdom, as well as seeing things more in a richer way. In any case, yes, I mean, especially over the course of the 20th century, when we were struggling to understand very small things, atoms and then atomic nuclei, where the experiments are difficult, and also to understand the universe as a whole, where again experiments are very difficult. We've had to not follow so much the Baconian ideal of gathering a lot of data and just correlating facts. If we want to make progress in fundamental understanding, it's been more, what's really worked is to make guesses about how the world might work, and then see if those guesses are supported by facts. But to interpret the facts, you have to have guesses that allow you to look for the right things, which are often quite subtle and require a lot of image processing, so to speak, as we look at the very small things or very large things. And it's been absolutely extraordinary that the guesses that were based on kind of aesthetic feelings about how the world might work or should work, to make the laws more symmetric, to make them more logically perfect, more unified, have turned out to be correct, that the world actually works that way. And, yeah, so
another. Sorry, I was just going to move on to another subject.
Yeah, go ahead.
One of the things you sort of just a gigantic subject which we could do 50 lectures on, was the idea of consciousness and the relationship with mind and matter. So obviously I'm not going to ask you to explain all of that just in like 5 minutes. But what I am going to ask, Monty was asking, where did you kind of read up on these things, or where, particularly the relationship between kind of mind and matter and the kind of molecular level of proteins and whatever's going on in our brain at the same time?
I've read quite a few texts on neurobiology. It's been an interest of mine for many years. In fact, when I was an undergraduate, I flirted with going into that subject, especially, but I liked mathematics, and at the time it wasn't really ready for mathematical treatment. Now, with the study of neural nets, it's getting there, and also quantitative biology, which we have much better probes and much more powerful ways of analyzing the data. But in any case, yeah, I followed that for many years. If you're asking what's a good introduction to these issues, I would defer to Francis Crick, who wrote a book, the great biologist, and who in the last part of his career was struggling with these questions of mind and matter. He wrote a book called The Astonishing Hypothesis, which kind of frames the question broadly. And the astonishing hypothesis, which he advocates for, is basically the hypothesis that mind emerges from matter. And why should we believe that? Well, there are many reasons, but let me mention two that weigh heavily in my thinking about it. One is that so far, people who studied, well, this one is actually two, that people who've studied the brain and studied psychology have always found that the brain is the basis of it. And when you injure the brain, you change the psychology and so forth. And neurobiology has really proceeded by assuming this astonishing hypothesis, and so far hasn't run into any showstoppers. So it might someday, but so far I don't think so. I don't know. And another aspect of that, which is kind of complementary, if you like, is that in physics, we often do very delicate experiments that require taking care of all kinds of possible effects that might distort the results. So we have to worry about stray radio waves, or we have to worry about tremors in the earth. We have to worry about the temperature. We have to worry about all kinds of things, but we've never had to worry about what the guy in the lab next door is thinking. There's never been a necessity to take into account effects of mind on matter. It would be a fantastic discovery if one could find such a thing. And that would be maybe the greatest discovery of all time in science. And it's a challenge to people who think that that there are souls that can control matter and so forth. Show me what is the effect? Give me anything. Those are two things. And the other thing is that in recent years, we've started to make minds, I would say. My computer beats me at chess, and the programs like AlphaZero have taught themselves by playing against themselves, learn to be the world's best chess and Go players. And these kinds of games were once thought to be among the highest intellectual achievements of people. And in those cases, and now we have with machine learning, we have ways of machines that can interpret images and really also create artistic images and create photographic images that seem very real. So they're doing very impressive feats that in a human we would certainly call mind and creativity. And for sure, those are based in matter because we designed them based on the principles of quantum mechanics, and which allowed us to make the transistors, which makes the circuits. And yeah, so we have lots of evidence that mind-like things can emerge from matter. We make them. And on the other hand, we have, despite, very delicate ways of inquiry, no evidence that there's something in mind that's separate from matter. And so I think, to me, it would be astonishing at this point if Francis Crick's astonishing hypothesis were not true. But but that is not a closed subject by any means, and there are certainly things we don't understand. And I think one of the great challenges, to me personally, I feel, is okay, so we have these fundamental laws which are stated in terms of quantum fields and mathematical relationships, and where am I in those laws? Where, they seem to be describing something very different from the world that I experience, and it's a very interesting challenge to find concretely how minds and the things, the way we experience the world emerges or not from our fundamental understanding. Because as I said, I think we understand matter well enough, the kind of matter that brains are built out of. We know what it is and how it behaves, we think, well enough. It's been very well tested. All our fundamentals are very well tested and seem complete. And so the question becomes well posed. This is an outstanding example of great answers leading to great questions. Now it's a concrete challenge. You have to, we have to put up, show how it works, right? And I think it's fair to say that in broad outlines, we've understood how metabolism works, which was once thought to be a kind of mysterious, special thing that life does. And we've understood how heredity works, which was also, and how that could empower evolution. But we don't understand really at the same level at all how mind works. And that's a great frontier.
I've just got a quick plug here. So Ashman Singh in the chat, who wasn't, who I don't know, said Mark Solms, the co-founder of neuropsychoanalysis, has just released his book, The Hidden Spring, The Source of Consciousness. And just coincidentally, he will also be speaking at the Royal Institution at the end of this month. So if you want to find out more about the journey to the source of consciousness, do join us on the 28th of January for that one at 7 p.m. GMT. Thanks, everyone. So I'm just going to...
By the way, I mean, consciousness is a very interesting subject that I do talk in a more specific way also about in the book. And there are very interesting experiments that reveal some of the intuitions we have about consciousness are actually not well-founded, or I would say just wrong. And a lot of what goes on in our brains is unconscious and is reported to us, and we think of it as we've willed something, but in reality, subconscious things have happened and reported what their results to consciousness, to a special kind of attention processing unit or modality that we think of as in control, but in actuality is just a a report for internal consumption about what our brains are experiencing and doing.
Just before we let you go, I've got a few more physics questions to round things off. Charles Parry asks, what are the most likely explanations of dark matter? And I guess by also asking that, you're kind of implying also dark energy as well.
Yeah, well, dark matter and and I didn't enter into the technicalities of dark matter versus dark energy, but astronomers have found two rather different phenomena that both affect, give gravity, give cosmic forces that we would call gravity. That's not due to the kinds of matter that we know, the kinds of matter that, as I mentioned, we understand very well, that participate in engineering and biology and chemistry. One is called dark matter, the other one is called dark energy. Dark energy is really the phenomenon that space has a mass. So space has a density, which seems to be the same everywhere. And this is a phenomenon that Einstein, in a way, anticipated, because it's a logical possibility within the general theory of relativity. It's the so-called cosmological constant. So we know how to fit it into our description of the world. We'd like to understand it more deeply, but well, that's one thing that we know how what it is. And unfortunately, I think our prospects for drilling down into space and sorting out everything that contributes to its density are very difficult, because space is very rich, seems to have a lot of structure, all of which is contributing to the density, some positive, some negative. And to really see why there's this imbalance, we'd have to have good control over all of it, and we don't. So that's an open question, with a much more accessible question, it seems, is this dark matter, which looks like some kind of new particle would do the job. It's a particle that has to have a certain class of has to have certain properties. We have certain experimental constraints. It has to interact very weakly with ordinary matter, of course, otherwise it wouldn't be dark. We would have seen signals from it, but with the tools of astronomy. It has to be produced in the Big Bang. It has to be stable. And physicists have come up with various ideas for what it might be. My favorite is something called the Axion, which I named and then sort of and invented for other purposes. It arose it didn't have dark matter in mind at all. It arose in attempts to make the fundamental laws more beautiful and comprehensible. It actually has to do with the understanding more completely the fact that the laws look the same, run forwards in time and backwards in time. And that may seem very tenuously connected to the dark matter problem. And it is, logically, but miraculously, it turned out that by addressing one problem, you're led to a very promising suggestion. You have to introduce this new particle, the Axion, which turns out to have exactly the right properties to be the dark matter. And so thousands of physicists around the world today are thinking about antennas that, or ways of observing this Axion. Supposedly it's the dark matter, so it's all around, with making more of the mass of the universe than ordinary matter, but interacts very weakly with our experimental tools. But the equations are definite enough that you can use them to test the theory. And well, it's hard work, and people are just now acquiring the technical muscles to really be able to do it. And watch this space. In the next 5 to 10 years, I will either rule it in or rule it out, I hope.
So just as
I hope we rule it in, but we might also rule it out.
So they can't take the Nobel Prize back, Frank. It's fine.
No, well, right. No, well, that of course has to do with something completely different, but you know, that's done, but we're looking forward to more stuff. And just I can't help but say, since we're talking, this is the Royal Institution and Faraday and Maxwell, that this was very much the situation with Maxwell's equations, which to me is a continuing inspiration. Maxwell tried to make the equations of electricity and magnetism as he knew them at the time, that came out of the work of Faraday, especially, into a mathematical system that was logically consistent and coherent and beautiful. And to do that, he found that he had to introduce a new effect, and in a sense, a new particle, a new kinds of electromagnetic disturbances that nowadays we call radio and infrared and microwave and gamma rays and X-rays. None of those were known at the time. And yet, by making the equations more beautiful, the equations were, those equations contained all those phenomena. And people had to design antennas that were capable of detecting them, because they don't appear to our senses. And so it was a very parallel kind of development. People had to work from the equations to develop the technology to detect the predicted effects. Heinrich Hertz said something very, who really was the first person to do that, and set the stage for radio technology. Said that you can't escape the feeling that these equations are wiser than we are, wiser than their creators. They contain more than was put into them. Yeah. So.
And just for my own head, the axion theoretical particle, that's a different thing to the graviton. Is that right? So the graviton is a different, completely different force carrying particle. That's yeah. Right. So because somebody else, Jerry Lynn, was asking, do you think we'll ever discover the graviton, and if so, how?
The graviton, well, I mean, the graviton is a particle that emerges if you apply quantum theory to gravity. So just as when you apply quantum theory to electromagnetism, you find that the electromagnetic field actually exists in units called photons, that the electromagnetic radiation can be thought of as made out of particles called photons. The quantum theory applied to gravity tells you that gravitational radiation should be made out of individual particles called gravitons. Now, the existing experiments on gravitational radiation, sensitive as they are, really are monitoring the effects of many, many gravitons acting together. So you can't detect whether there's one more or less based on the response of the LIGO detector or any existing experiments. But there's hope, I think, and that's one thing I'm working on these days, is that there may be effects that are more complex than have been taken into account so far in the theory of gravitational radiation, where quantum mechanics really plays an important role. I think these could arise in the last moments of black hole mergers, which is one of the things that's studied at these detectors. And because quantum mechanics becomes important in theoretically in those regimes, I'm thinking hard about ways that might be accessed experimentally. But that's the future. At present, there's we have good theoretical grounds because it's the logical synthesis of quantum mechanics and gravity leads us to predict the existence of gravitons, but so far there's no direct evidence for the effects of individual gravitons.
Fantastic. So I think we'll start to bring things to a close, but I'd be remiss if I didn't give a shout out to everyone who's been chatting away in the live chat on the side. Thank you very much for all of your comments. I'm really sorry we haven't been able to get through everything. There's been a few. I'll be honest with you. I'm not a professional physicist, but there's been a few people in the chat that have maybe been suggesting alternative theories or their alternative view of physics. Which, you know, far be it from me to disagree with your view of physics, Frank. But some people have taken it upon themselves to come up with their own interpretations. Somebody who's calling themselves the Time Lord says that the relativity and quantum mechanics seem incompatible because of the false belief that time slows down near massive objects. It doesn't. The measurement of time is slowed down. Now, I just wonder if you'd like to comment on that, and how would we know if it was the measurement or the thing itself? Because how would you know without measuring it?
I'm not sure exactly what that means.
But time does slow down near massive objects.
If all measures of time indicate that it's slowed down, I think it's a matter of language more than anything to say that time itself has slowed down. If there's some independent meaning to time slowing down, that has to show up in some kind of measurement. And okay, I mean, it's a very interesting hypothesis that there are ways of distinguishing what's happened to time around massive bodies than the ways we presently know, which, well, to a first approximation, can all be described as saying that time slows down. There may be other manifestations, but I don't know of anything in our present understanding of fundamental laws that suggest that. And I might mention that there's a lot of evidence for time slowing down, and that effect being correctly described by general relativity and even its intersection with quantum mechanics. These are things like the Pound-Repka experiment. Also, when computing distances in the GPS system, you have to take into account that time slows down near the surface of the Earth, and to get really accurate results, you have to do that. And if it were wrong, GPS would fail in significant ways. So there's a lot, and there's also evidence from stars when you have emissions of light from nearby heavy objects, the spectral lines are shifted. You know, so it's not a theoretical fancy that there's this time dilation that's usually described by the idea that time slows down. As I said, there might be other effects, but I don't know what they would be without more specific suggestions. And so most of us, most practicing physicists, as far as I know, all of them would say that time slows down.
Fair enough. So I think that's pretty much it. I've just got a few more things to go over before we finish the stream. Just a reminder to everyone out there that the Royal Institution is open for you to join. If you like what we do and you want to support our work, please do consider becoming a member. All the information is on our website, rigb.org. There's also a suggested donation of £10 if you've enjoyed the stream, want to hear more from us and want to keep us going for another 222 years, then that would be much appreciated in these very trying times. A lot of our money, you might know, comes from hiring out our building, running events, selling tickets, all that kind of stuff that we can't do at the moment. We don't get any money at all from the UK government. We're completely independent, but that means we're obviously in a bit of a sticky situation without the ability to generate as much revenue as we used to. So if you can spare the money, really appreciate it. It would be really appreciated by everyone at the Royal Institution. Don't forget the talk from Vicky Pope on Thursday, all about climate modelling. Frank, obviously your book's launched today, but would you like to remind people of some of your other fantastic books that you've written previously, some of which you can see talks about on the Royal Institution YouTube channel?
Well, I've written my most recent book until this one was called A Beautiful Question. And as I said, it's about, broadly speaking, beauty as, first of all, what it is in terms of human history and how it's been realized in different cultures, and the parts some forms of beauty have deep relationships to our understanding of the physical world and have been an impressive guide to making progress in understanding the physical world. That's the theme of that one, and it ranges over a lot of history and a lot of culture. This most recent book, as I said, is kind of in the other direction, starting from truth and spinning out its implications, beautiful or not, but I would say on the whole beautiful. I also wrote a book called The Lightness of Being, which is a full explication with as much as it can be done without actually going into the mathematical details, but doing real serious work with the concepts, that most of our mass that you find out when you weigh yourself on a scale, most of the mass of our bodies, 99% or more, is based on energy, based on interactions of quarks and gluons that we understand on the basis of a very beautiful theory. And so we understand how mass arises from energy, kind of reversing Einstein's idea that energy can arise from mass, or running it the other direction. And this is not so. It's not an exotic phenomena. It's us. this origin of mass in energy. And then I wrote a long time ago with my wife Betsy Devine a book called Longing for the Harmonies. That's a wide-ranging discussion of physics and cosmology. That's also very good.
I'm sure.
A little dated in parts now, but it touches on many of the same things as fundamentals, but in a less philosophical way and a little bit more technical, but also meant to be accessible to the public. Then I've written a couple of technical books also, but probably, well, those I'll leave you to explore on the internet, I think.
Oh, that's absolutely fantastic. And I've just noticed you're also on Twitter at Frank Wilczek.
Yes.
So
yes.
do head over to
I'm
that
not as active
page.
as I once was, but yeah, you'll find some good stuff there, and not too much bad stuff.
Well, do consider giving him a follow. And just remains to me to thank you all for your amazing questions and for joining us tonight. And a big thank you to Frank for just an absolutely fascinating talk and discussion. Thank you so much, Frank.
Thank you. Thanks for the opportunity. And I said, it's always a joy and an honor to stand, or, well, I'm not standing where Faraday stood, but sort
virtually.
of to, yes, that's right, to sort of commune with that spirit. Yeah, thank you.
Well, thank you so much, Frank. Take care, everyone. Good night.